So we've now gone over our 4 different conic sections. So remember those were circles, parabolas, ellipses, and hyperbolas. And then we also looked at how to solve nonlinear systems. And all of those things are items that we're going to need for our planetary motion project. But I wanted us to look at a couple of just like application type problems. So this is all just going to be material that we've already covered, but we're now applying it to put it in context with different applications. And specifically in this case, we're going to be looking at different space applications. So this one says, use the labeled points on the outline of the circular crater on Mars to estimate its diameter in kilometers. Assume each unit on the coordinate system is 1 kilometer. So there's a couple of important things from this problem that we can kind of look at. First, I would like us to point out that notice that each unit they define to be 1 kilometer. Now, when we're doing our spatial project, we're talking about traveling in space, and so we're going very, very far distances. So when we create our units, you're probably going to want to make it probably like thousands of kilometers to be your unit. Otherwise, you're going to start getting really, really large numbers. You can also use scientific notation like we've been talking about in physics. But for some of the math equations, it's going to be a little bit easier if you don't have to worry about the scientific notation. So in that case, you would want to make your unit thousands of kilometers. But in this case, since we're just talking about a crater on Mars, we can go ahead and stick with the unit of 1 kilometer that they give us. So then the next thing that's important to point out is that this is going to be a circular crater. So that's important because now we know that no matter which 2 points that I pick on my circle, they're going, as long as they go through my center, they're going to be a diameter. And this tells us that it is a diameter, or that we can use these to estimate our diameter. So we're specifically looking for the length of that segment right there. So then the other thing that this problem is good is it's going to remind us of our distance formula. So remember that distance equals x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So I'm going to go ahead and use my 5 as my x2. So I would have 2 minus 13 squared plus 5 minus a negative 4.5 squared so we get negative 11 squared plus 9.5 squared, which is going to give us 121 plus 90.25, which is the square root of 211.95, which is approximately 14.53. And it's important to label our unit, so that would be kilometers. Now, to kind of take this a step further, if we wanted to find the equation of this circle, we would need our midpoint. And we can find that by using our midpoint formula between our 2 points that they give us. And then we could divide our diameter by 2 in order to find our radius, because remember that our formula is x minus h quantity squared plus y minus k quantity squared equals r squared. But in this case, they don't ask us to do that. They just ask us for the diameter, so that is my answer. So let's look at another example. This one tells us Apollo 8 was the first manned spacecraft to orbit the moon at an average altitude of 185 kilometers above the moon's surface. Write an equation to model a single circular orbit of the command module if the endpoints of a diameter of the moon are at 17,040, 0 and 17,040, 0. Let the center of the moon be at the origin of the coordinate system measured in kilometers. So, we need to first probably give ourselves a little bit of a diagram. That's going to be a little bit helpful. And so like I talked about in one of our examples previously, remember that when we're picking where our points are, it's going to be really easy, or to make our lives a whole lot easier, if we choose for the centers of some of our objects, or for our centers of our hyperbolas or different conic sections to be at 0, 0, because it just makes the whole equation much easier to find. So here in this case, we know that the center of the moon is at 0, 0. And then they tell us that I also have a point at, they said 1740, 0, and in the other direction, it will be at negative 1,740. Comma 0. And we know that that is going to be the diameter of the moon, and we're kind of assuming here that our moon is going to be a circular shape. From there, okay, we want to basically look for something that is in orbit around the moon, and they tell us that it has to be 185 kilometers above it. So we would be here. Now the key to writing this equation is going to be to find our radius. So remember, for our circle equation, like we just said, it's going to be x minus h quantity squared, but because my center is at 0, my h is at 0, and then it's going to be y minus k quantity squared, but again, we're at 0, so we just have x squared plus y squared equals r squared. So the important thing is going to be to find that r squared. And really, the biggest thing that we're going to need to do here is notice that from my center to the edge of my moon is going to be a distance of 1,740. But because we're wanting to write an equation to model the orbit, we need to write an equation for the red one, which means that we need to take into account that we have to be 185 more kilometers outside of our moon. So our r is going to be 1,740 plus that 185. So we get 1,925. But that is our r, not our r squared. So then we will plug that into our handy dandy calculator and square it. And we're going to get 3,705,640. Now that's the first way that we could do it. When we're looking at our project, and we're going to look at one more example that's kind of like this. So because we were just talking about the orbit around this moon, it was okay for us to take into account the diameter of the moon itself. But when we're traveling through space, we're going to be going hundreds of thousands of kilometers. And so at that point, the diameter of the moon really becomes like so small compared to how far we're actually going, that we go ahead and just pretend that it's just a single point. And so what I mean by that is I'm not going to take into account my diameter. So I'm just going to say that my moon is centered at 0, 0. And basically I'm going to treat it as a single point and not worry about what the diameter would be of my moon. So then at that point, the only thing I have to worry about is that I need my orbit, we said, to go 185 kilometers. So this would be 185, 0. This would be negative 185, 0. And this would be my orbit around my moon. So they're kind of under the same assumption. Okay, so my x squared is still, or my k and my h are still going to be 0, so I still have x squared plus y squared equals r squared. But the only difference now is this time my r is just going to equal 185. And so we end up with x squared plus y squared equals 34,225. And so this is the way that I want you to do it for your project. I want you to treat each of your planets just as a single point and not worry about what the diameter of the planet is. Because it's not going to end up mattering that much when we do our equations, and it makes our lives a whole lot easier when we're trying to find our equations. So let's look at another example. This one says Earth's orbit is about 91.4 million miles at perihelion and about 94.5 million miles at ephelion. Determine an equation relating Earth's orbit around the Sun in millions of miles with the center of the horizontal ellipse at the origin. My text got cut off, so it should say at the origin. And I believe that you talked about your perihelion and your ephelion in physics, and I'm sorry if I pronounced those wrong. But remember that those are basically going to be the shortest and farthest distance from your Earth's orbit to your Sun. Okay? So remember that when we're talking about our elliptical orbit, so this is going to be our elliptical orbit. So they tell us that it's a horizontal ellipse, which is why I drew it longer going left and right than it is up and down. Now, realistically, your orbit is going to be much closer to a circle than that is, but it just makes it a little bit easier for us to see if we kind of over-exaggerate it. Okay? Now, remember that I have my center, and they tell us that we're going to put it at the origin, which is nice. And then we're going to have two foci. And remember from physics that when we're looking at orbits, one of our foci is going to be the Sun. And then the other is just kind of going to be an imaginary point. So they give us two different values. Okay? They tell us that the shortest distance, okay, which is the perihelion, is going to be 91.4 million miles. And then they also give us our farthest distance, which is going to be, we said 94.5 million miles. Now, notice that because we're centered at 0, 0, our foci are also going to have to be along our x-axis, which is nice because then everything kind of lines up. So notice that the length of my major axis is going to be those two things added together. And this is going to be important because remember, we need to find our A and our B values in order to be able to plug into our equation. So again, we've centered ourselves around 0, 0. So we're just going to have an x squared and a y squared. And remember, it equaled 1. But then we need to figure out what A and B are in order to complete our equation. So the reason that I found the length of my major is because remember that the length of your major axis also equals 2A. So now we know that 2A equals 185.9. So we can divide by 2 to both sides and get that A is 92.95. We're then going to square that and we get 8,639.7. The other thing that we kind of need now is we either need to be able to find our B value, which remember is the distance to our co-vertices, but we don't have a whole lot of information about going up and down. We really only have stuff going horizontal. But remember that we can find our C value, then we can use that equation that we know to find our B value. Now something to notice is that from my sun to the outer vertex is going to be 91.4. And we've also labeled our A value, which is going to be, all of this right here is A. So notice that if I take my A value and I subtract that perihelion, I'm going to get my C value. Because remember, the C value is the distance from the center to the focus. So we would take our A value, which is 92.95, and subtract our P value, which was 91.4, and we get 1.55. Now remember that that's not our B value, that's not what we want to plug in to our equation, but remember that we had this C squared equals A squared minus B squared relationship, and so this is going to allow us to be able to solve. So we would square 1.55, subtract 8,639.7, and we are going to get 8,637.3, and that's going to equal B squared. So then I'm going to take the square root. And I get 92.94. But remember that what I want to put into my equation is going to be B squared. So that's going to be 8,637 point. And so notice that our A value and our A squared value and our B squared value are really, really close to each other. And so that's why I said in this case, our orbit is going to be really close to a circle, just not quite a circle. So our shape over here should actually look like something more like that, where we're going farther left and right, but it's just barely noticeable. So let's look at another example. So this one says Earth and the Sun are 1.46 million kilometers apart, and a comet follows a path that is one branch of a hyperbola. Suppose that the comet is 30 million miles farther from the Sun than from Earth. Determine the equation of the hyperbola centered at the origin. And so they kind of give us a picture. I'm not a huge fan of this picture because they kind of draw us a triangle instead of drawing us a hyperbola. But my comet is going to get really, really close to our Earth and basically kind of slingshot. Going to be a little bit hard to draw, but slingshot back around. So that's what our hyperbola would look like. Again, just roughly drawing that in there. So, because, again, we made our lives easier on ourselves and we centered everything at 0, 0, we're going to have x squared. So notice that we opening left and right minus y squared equal to 1. And so we're going to need to find our a and our b value. Now, notice that they tell us that the Earth and the Sun are 146 million kilometers apart. And so, because again, drawing is not super great, this really should be my center, okay? So if that's my center, and I know that the distance from the Sun to the Earth is 146 million kilometers, and I'm using both of those as foci for this, then we're going to say that we can say that our C value is going to equal 146 divided by 2. So that's going to be 73. So that's kind of helpful. Now, the next part is going to take a little bit of kind of imagining with me, okay? So, notice that they also tell us a second thing, and that is the comet is 30 miles farther from the Sun than from the Earth. And so what we're trying to find now is our A value. So basically we're needing to find the distance to one of our vertices. But because it's symmetric, it's going to be the same to either one. And we're going to need to use the fact that we're 30 million miles farther from the Sun than from the Earth. And what we're going to do is notice that this comet, right, is going to be moving in this orbit, right? And it's saying that no matter where the comet is always 30 million miles farther. Now what we're going to assume is that that comet is going to reach the point of my vertex. And why we do that is because then everything kind of lines up really, really nicely. Okay? So again, like I said, kind of bear with me for a second. Okay? So, like I said, we're going to pretend that this value right here is x. The distance from the comet to the Earth is x. And why we do that is because then we know that the distance from my comet to my Sun would have to be x plus 30. But also notice that our hyperbola has to be symmetric. So this distance right here has to be x as well, because that would be to our other vertices. So those two have to be the same. Well, notice that if the whole orange part is x plus 30, and my blue part is x, then we know that the portion in the middle has to be 30. And that's the important part. And so now remember that that's going to be the length of our our transversal axis. And that's important because remember that that is 2a. And so that is our length. So we can set 2a equal to 30. And then we know that a equals 15. And then just like before, once we have a and c, we can use our relationship that we know in order to solve for b. The important thing to remember is that with our hyperbola, it's a squared plus b squared, and with our ellipse, it's a squared minus b squared. So we get that b equals approximately 71.44. So then if we take a value and square it, we would do 15 squared is going to give us 225. And then our b value, which was b 71.44, if we had squared that, it's going to get us back to that 5,104. So notice that our b value in this case is much bigger, which is why it's really going to be a wide parabola, because it has to go out really far away from our Earth. That we get. The thing to be careful about is if you look at this problem in the book, our answer is going to be slightly different than the one that we got. And the reason for that is going to be that the book takes into account the diameter of the Earth. And we didn't. So our answer is going to be slightly different, but like I said, in the grand scheme of things, that diameter isn't going to affect the equation itself or the path of the comet itself very much. And so we just kind of pretend that we're just looking at a single point there. Next problem. This is one of our homework problems, and it says 2 satellites are placed in the orbit about the Earth. The equations are orbits, and then gives you our 2 equations. And it asks you to use a graph to figure out what those points of intersections are. And that's fine, except for when we're needing to prove something exactly, we need to be able to do so algebraically. But the problem with these is that you end up with some kind of ugly decimals, and so for us to try and do that algebraically, would it be super fun? So what I'm going to do instead is we're going to look at this very similar problem, but instead, we're going to say that one of them has an elliptical orbit still, but then the other one is going to have a hyperbolic orbit instead. So, I'm going to keep my first equation the same. So, x squared divided by 300 squared plus y squared divided by 900 squared. But I'm going to change my second equation to be y squared divided by 900 squared minus x squared divided by 600 squared. So I changed this second equation to a hyperbola instead. And I'm still trying to find where these two equations meet. And we need to prove it using our solving steps. Now hopefully we notice that our y-squareds are very, very similar. And that's why I went ahead and changed it to a hyperbola, because it's going to make it a lot easier for us to solve. And this is going to be similar to what you're going to see on your project. So notice that if we were to graph these, basically notice that our 900 squared is going to be bigger, so that's going to give us a vertical hyperbola. And because my a value for my hyperbola is the same as the a value for my y, our vertexes will be the same, which means that they should meet at our vertices. And we're just going to prove that algebraically. So I'm going to multiply one of my equations, it doesn't matter which one, by a negative. So when I do that, I end up with a positive x squared divided by 600 squared minus y squared divided by 900 squared equals negative 1. So notice that when we add those two things together now, my y's are going to go away. And so we would only have x squared divided by 300 squared. And then we're going to add x squared divided by 600 squared equals 1 plus negative 1 is going to give us 0, which is nice. Now, 1 divided by 300 squared is going to be a very small decimal. And then if I were to add to that 1 divided by 600 squared, which is also a really small decimal, I get a slightly larger decimal, but in the end, I have 0.1, 2, 3, 4, 1, 3, 8, 8, 9, x squared equals 0. So both of those are x squareds, so if I add my fractions together, I can combine them, and that's the decimal that we get. And the reason that we're getting such a weird decimal is because notice that these distances are in kilometers instead of like thousands of kilometers or something else. But that's okay, because the nice thing is, notice that if I divide both sides by my really ugly decimal, I'm dividing 0 by that really ugly decimal. So I still get 0 on the right-hand side. So x is still going to be 0, which is a lot nicer to deal with. So then I'm going to pick an equation, and plug in 0. So I'm going to use my first equation. So if I plug in 0, now I need to solve for y. Notice that this whole first fraction is just going to go to 0, which is nice, it goes away. So then I just have y squared divided by 900 squared equals 1. So now notice that when I multiply both sides by 900 squared, well, 1 times 900 squared is going to be 900 squared. And then I can take the square root of both sides. So I just get 900, because my squared reduces with my square root, but remember that we have to put a plus or a minus. So we're going to get 2 points, 0, 900, which makes sense because if this is at 0, 0, which both of them are centered at, it's all going to line up, and so we will have only gone up and down and not any left and right. And so those would be the 2 points that they intersect at. And like I said, you're going to use a very similar process, but you're going to be creating the equations on your project, but it's really going to be easiest if you choose those points so where our vertices line up, because then, like I said, it makes solving things much, much nicer.